Well, hello everyone. We are reaching the equator of the conference, and I think we are very satisfied about the level of the presentations, the posters, and the discussions. And we hope they will finish in the same high note. Toshi and I will present now the second and third invited speakers out of the total of 4. We are particularly excited to present you this session because it was always clear in our minds that given that the host, us, Observatory of Yebes, is a radioastronomical site, we wanted to do something related to that, and by extension to the VLBI for geodetic applications. If you are anything like me, laser rangers, you know that VLBI is a thing that exists, and somehow by a sufficiently advanced technology indistinguishable from magic, they get images of black holes or results of geodetic interest. So hopefully we will, with these 2 speakers, Pablo de Vicente and Rudiger Haas, they will cast some light on this mystery of VLBI and radioastronomy. I will present the first speaker now, and Toshi will do the same for the second one, Rudiger. And so we will have here with us Pablo de Vicente, who's been the director of the Observatory of Yebes since 2017. Now, to the surprise of no one, Pablo is an astronomer whose first interests were focused on the star formation and the determination of physical parameters in molecular clouds from spectral observations. Now, his field experience was later on gained on the IRAM 30 meters telescopes in Spain as a support astronomer, and then he moved on to the Max Planck Institute for Radioastronomy in Bonn, in Germany, where he joined the VLBI team. And all that experience then was imported back to here, and Yebes Observatory then joined the EVN network, the European VLBI network, with 2 of his existing antennas. Pablo led the software development and was head of the commissioning of the Yebes 40-meter radio telescope and the 13 meters that you will see this afternoon. He was then later on the coordinator of the 40-meter radio telescope and head of VLBI operations. Among the tasks that he carried out, we can include the software development of the telescope control of the 40-meter telescope, and then he moved on to being the coordinator and head of operations, and he's got ample experience on radioastronomy, observations, operations of single dish, VLBI, backend telescope control software again, and data reduction and exploitation. Now, he will vehemently deny this, but I have it in very good authority that he is one of the best and most competent software developers that we had the luck to have at Yebes. Unfortunately, now he's very busy directing and managing the observatory and being part of various technical groups and working packages and advisory committees, such as the advisory committee on the Narita and Hellenic telescopes and part of the directing board of the International VLBI service. Now, Pablo is going to give us an introduction on radioastronomy, focusing on the work done here at Yebes, and I hope you will join me here and thank him for his presence and the talk he's going to give us.
Hello. I was not expecting such an introduction. Okay. I will not use this microphone because I usually move a lot, and maybe the microphones are not going to pick properly my voice. So let's see. Okay. So hello everybody. I have changed the title of my talk. Don't panic, Beatriz. Okay. Yeah, it's a tiny modification. It was originally radioastronomy at Yebes Observatory, and I said radioastronomy and Yebes Observatory, which means that these tiny modifications means that I am going to talk a little bit about radioastronomy. I will make a very short introduction, and then I will introduce you to Yebes Observatory. So radioastronomy, what should I do with this? Now, okay, good. So radioastronomy is a quite young field of astronomy. It is only 90 years old. But of course, compared to several thousand years for optical astronomy, it can be considered young. And the first steps were done in the United States by Karl Jansky. He built an antenna which was turnable, and he discovered radiation at 20 megahertz from the center of our galaxy. Later, Grote-Reber, also in the United States, followed his tracks and decided also to build a radio telescope in the backyard of his house. And he also discovered radiation from the galaxy, from the Milky Way, and he made the first radio map of the galaxy. And after World War II, radioastronomy progressed. It developed continuously, and it is nowadays one of the pillars of astronomy. So which is the realm of radioastronomy in the electromagnetic spectrum? Well, the wavelengths go from several meters to some millimeters. And the lower end is limited by the ionosphere. I mean, we have here an atmospheric window in which we can work. So the lower end is limited by the ionosphere, and the upper end is limited by molecular oxygen and water vapor. That's the reason why submillimeter observatories are usually located at dry and very high sites, like for example, ALMA, the Atacama Large Millimeter Array. So in our case, in Yebes, I had a visit yesterday, and one of the questions was, which is the height of Yebes? Well, Yebes is more or less 1,000 meters, which is okay. Not good for some millimeters, but it is okay for 3 millimeters, which is our highest frequency. I'm going to show you now a picture of a certain region of the sky. There's nothing special of this image. You can see the dark brown, some stars, and this region is the galactic center. And probably you know that between us and the galactic center, there are dusts of cloud, which are like a curtain. We cannot see what you have behind. So I'm going to show you what radio is showing us. This is the image. This is a gorgeous image from my point of sight, and from my point of view, sorry. And this is from MERCAT. This is an array in South Africa, 64 antennas. It is at 1.3 gigahertz. And you can see here supernova remnants. You can see filaments, arcs, star formation, collision of clouds, and of course the star, which is Sagittarius A star, which is the black hole of the galaxy. So I think I have convinced you that radioastronomy is revealing us with something that the eye could not detect. Radioastronomy is showing us a universe which is highly energetic, and it is also cold and dark. I will show you that later. Which phenomena produce this emission? I have divided the emission in continuum and spectral. And in the continuum one, you have emission from the breaking, the deceleration of electrons in an electrostatic field. An electron which has a curved trajectory, it releases photons, and the photons are detected in radio. And then there is a very famous one, which is synchrotron. Synchrotron is when you have magnetic lines, magnetic fields. Electrons go twisting around the magnetic fields. They go at relativistic speeds, and the radiation that they emit is very beam, very focused, and it is very bright. And I'm showing you an example of that. That is Hercules A. Those are two jets which move at relativistic speeds. And at the center, there is a very famous black hole, which is M87. I will show you a picture of this black hole a bit later. This image is taken with a very large array in Socorro, in New Mexico. Then, of course, there is another continuum emission, which you will know, which is the Blackbody. But in radioastronomy, we usually study emission from Blackbody sources which have low temperatures, like, for example, the interstellar dust or the circumstellar dust. They are usually at tens of Ks, maybe 20K, 30K, 10K, and then they peak in the infrared. But you can catch the emission at the tail, at the laser is here, at this tail, in the millimeter regime, like for example, in this case. This is an image from the Atacama Large Millimeter Array of a stellar system in which you can see a ring of dust around the star. So this is an example of how radioastronomy is also showing us the dark universe that it is not visible to the eye. And then we have a spectral also emission, which comes basically from two sources. One are rotational transitions from molecules. I have depicted here a carbon monoxide. Carbon is the black ball, and oxygen is the blue one. They rotate. Well, this is not very accurate, but the change between two rotational states release a radio photon. In this case, it is 115 gigahertz. If the molecules are heavier, you get radio photons at lower frequencies. And this is a very abundant molecule. It is the most abundant molecule after molecular hydrogen in interstellar space. And then you get also radio recombination lines, which are, they come from places, well, where the environment of high energetic stars, O and B stars, they ionize the environment around, and the hydrogen, the hydrogen has lost its electron, it recaptures it again, and then it goes through a cascade of levels, and the upper levels have a small difference, they have a small difference of energy here, and they release here radio photons. I'm going to show you a spectrum taken with the 40-meter radio telescope at Yebes. You can see this is the first one is 20 gigahertz, and this is another band, 40 gigahertz. All the blue lines are radio recombination lines, and the black ones, this is ammonia, for example, come from rotational transitions. This is, for example, silicon monoxide. Let's go just a small glimpse of what the techniques or the technology that we use. As in optical telescopes, we use paraboloids because a planar wavefront is converted into a spherical one, and you can place your receivers, we can place them at the primary focus, at the secondary focus, or at an azimuth focus. The telescope, the radio telescope in Yebes is an azimuth one because it is more comfortable and we can manage much better the maintenance of the receivers. There is something which is very important, and it is that receivers, well, first I will tell you what the receivers are. Receivers are devices which amplify the radiation just to decrease the noise. Then they down-convert the frequency, keeping the phase and the amplitude, and then they are sent to a backend room where they are sampled and digitized, and then we can analyze them. These receivers have to work at very low temperatures, which are 15K or 4K or even millikelvin if you use kits, for example, which are special devices. And they usually traditionally they detect both polarizations, maybe right and circular or horizontal and vertical. But in the last decade, we are trying to put feeds in the focal plane. But this is very complex because try to imagine that if you have a small telescope and you are looking at wavelengths which are this size, you cannot pack several feeds there. So there is a very big difference with the optical CCDs. You don't have a place where you can place a CCD, a location where you can place a CCD to get an image of the sky. I will tell you how we solve this to get images on the sky. And then I would like also to mention that we have several limitations, which are the atmosphere, the water vapor. I mean, we can observe 24 hours a day, but if you are observing, for example, at 3 millimeters and it is raining, you better not observe. So rain, water vapor, and molecular oxygen are a problem. And then we have an increasing problem, which is very severe now, and it will get worse, which is radio frequency interference, which comes from mobile phones, wireless, radars, and now constellations of satellites like the Elon Musk one, Starlink. Yeah, it is not our friend. And there is one parameter which is very important, but it is also, this is common in all astronomy, which is angular resolution. You know that it depends on wavelength and the diameter of the telescope. The larger the telescope, the higher angular resolution you get. You are also more sensitive, but it is very important that you get a better angular resolution. That's why we like to have big telescopes. I was telling you that how do we make images of the sky? What we do is we have a single pixel. What we do is, for example, for a point-like source, we drift the telescope on top of that, and then you get, you can imagine that this is the power when you go across the source. You get these peaks, which are usually a Gaussian. You can do this with extended sources. These are maps that we made with a 14-meter radio telescope, which is no longer working. These are old maps. And then from the 30-meter. This is the galactic center, the one that I have shown you before. Well, if you want to make images, of course, you are not going to use a single dish. It is much more efficient to use an array, an interferometer. And an interferometer is a collection of radio telescopes that observe simultaneously. These telescopes can be connected through a cable sharing a reference, a frequency reference or a clock reference, like, for example, the VLA, you can see here, or they can be disconnected. They do not share a clock reference or a frequency reference, like the BLBI, in this case. So what do? What we do is we have a pair of antennas, we receive the signal arrives later to some telescopes, and then you shift the signal, multiply the signals only, and integrate for only 2 seconds or maybe up to 2 minutes. That depends on the stability of the atmosphere. And then you get a lot of points with different baselines, orientations of the baselines with respect with the source. And you perform then a mathematical operation and get an image. I will show you in the next slide. What it is important about the interferometer is that the angular resolution that you get is the maximum distance between the telescopes. And the highest angular resolution that we have ever achieved in astronomy comes from radioastronomy. And in fact, the first interferometer in astronomy was a radio interferometer, although the interferometers, of course, were well known in physics before. The Michelson and Morley interferometer is a well-known device, or experiment, I would say. So just take the idea that the interferometers can provide images, and you get very high-resolution images from them, like this one. This is M87. This is at the core of the Hercules A radio galaxy that I showed you. And you can see these lines here. These lines are polarization. This is because this image was taken with 2 different polarizations, and you can see how the magnetic fields are working in the center of the galaxy, in this M87. Of course, well, I have to say that I said something which is not accurate. This is not the black hole. This is the shadow of the black hole, of course. This is the material that is rotating around the black hole. This image was taken with the HD, which is the Event Horizon Telescope. You cannot see probably from there which stations are, but are the blue lines. And then you get another parallel network in which we take part, this yellow one, which was the observations were performed at 3 millimeter, at the wavelength of 3 millimeter, at 3 millimeters, sorry, I was blocked. So how do you get a coverage of the whole Earth? You use the rotation of the Earth, but I'm not going to discuss about this because this is rather complex. And then there is a derivative, well, there is a connection with geodesy. And it is, you can use interferometers also to measure the Earth. There is a geodetic connection, but I will say nothing because I guess that, Rudiger, you are going to say something about that, I guess. At least you will make an introduction. Oh, okay. And of course, our goal is to have baselines which have an accuracy of 1 millimeter more or less. We have not achieved that yet, but this is our goal. And we contribute, of course, to the Earth orientation parameters, to the International Terrestrial Frame, and to the International Celestial Reference Frame. So let's go now to Yebes Observatory. What has Yebes Observatory have to do with radioastronomy? Well, we are a radioastronomical observatory, of course. But not only. We are also a technological development center for radioastronomy, and we will become a future geodetic fundamental station. So this is a picture of taken with a drone last spring of the observatory. Today is raining. This is a much nicer picture. You can see here we have the 40-meter radio telescope, the 13-meter radio telescope, and inside this radome there is a 14-meter telescope which is no longer in use. And you can also see some optical telescopes, this astrograph, and a solar telescope here, and the SLR which will come here. Beatriz has already shown us from a photograph taken from above. So the first observations were performed in 1979 with single dish at 7 millimeters. And then we decided that we wanted to take part of the European BLBI network, and the first fringes were achieved in 1989. And then we decided that we wanted to do geodetic observations. The geodetic observations are the classical ones are done at S, which is 2 gigahertz, and 8 gigahertz, which is X-band. I have depicted that in this spectrum, which is in logarithmic scale. This is S, this is X, and this is 7 millimeters. So we were covering this part of the spectrum. The receiver was designed in-house and built in-house, also the control system. And then we have the flagship of Yebes Observatory, which is the 40-meter radio telescope. We have an open skies policy, which means that any scientist across the world can submit a proposal to the telescope, and they are evaluated by a committee based only on merit. We have 2 calls every year, and we have the pressure for using the telescope is increasing. This policy of open sky is the one, I will mention that later because Beatriz also mentioned it in her talk. It's the one that has provided us with funds. I will say that in my last slide. It operates also as an interferometer element. It belongs to the European VLBI network and to the global millimeter VLBI array. And we also observe within the IVS. But we have been observing since 2008, and we are going in the next year. No, next year will be the last one that we observe with geodesy because we are transferring all the observations to a devoted telescope to geodetic observations. Receivers, as in the previous case, have been designed and built in-house, and they cover this part of the electromagnetic spectrum. I am going to show you 3 results from the 40-meter radio telescope. This is, the telescope is devoted mostly to astrochemistry, detecting molecules and looking at molecular clouds, making maps of those, looking at determining the physical and dynamic conditions in these molecular clouds. This is, for example, a spectrum of 3 objects, 3 sources, and you can see there are many molecular lines here. And well, the most important result for us is this one. You know, there are in the space there are molecules. It is not empty. There are atoms and there are molecules. There are around 260 molecules, and 20% of the molecules have been discovered in the last 2 years. And these 20% have been discovered by the 40-meter radio telescope. You can see that the discovery of molecules started in 1970. And you can see this is the contribution from the 40-meter radio telescope. So we are in the 2nd place now, and we are approaching the 30-meter radio telescope, which is probably the best telescope in the world in its frequencies. Then this is another result. This one comes from being part of the global millimeter VLBI array and also of the European VLBI network. This is again M87, our friend, this black hole, and we have participated in several observations to map the surroundings of the black hole. And this is not very beautiful, but it is a very important result. This is the first electromagnetic emission detected by radio telescopes after the passage of a gravitational wave. And this is due to the fusion of 2 neutron stars. And this was detected by radio telescopes all across the world. So this is a global observations in which we took part. So now let's come to the 13-meter radio telescope. This is the telescope that is devoted to geodesy. It started operations in 2016. And it is taking part now in the VIGOS project. It's also an element of the RAEG. RAEG is a network which is composed of 3 antennas located in Spain, in the Canary Islands, and in the Azores Islands, which belongs to Portugal. Maybe there will be a 4th antenna in another island in Flores, in the Azores Islands. It is the first telescope, and now there is another telescope operating, which is the Santa Maria one in the Azores. The Gran Canaria telescope will be probably available within 2 years. We are using a receiver also designed and built at our in-house, and it covers a wideband. It goes from 2 gigahertz to 14 gigahertz. Yebes is also a technological development center, as I said, and mostly of the developments are performed in this central building, which has different stages because they were built in different years. And we also have an anechoic chamber here. Yebes Observatory, in the old times, it hosted astronomers and engineers, but the staff grew, and then the astronomers moved to an infrastructure, to a building in Madrid, and engineers and technicians remained here. So I will devote just 4 slides for this. We are very well known in the radioastronomy world. We have an experience of 37 years of development in techniques for radioastronomy. We have, for example, just to give you an example, we have provided all the IF amplifiers for ALMA for 2 bands. There are 64 antennas in ALMA. We have provided them. We couldn't build them, so we transferred this technology to a Spanish company. We have also taken part in some space missions like Herschel. We were contributing to one of the instruments, which is HIFI. And we work with the European Space Agency, the European Southern Observatory, and other radioastronomy observatories in Europe. In particular, we take part in asking for funds to the European Union, and we go together with the rest of our colleagues in Europe. And some of the developments that we perform are also used for non-radioastronomical goals, like, for example, quantum computing. The amplifiers can be used for that, and dark matter, the detection of dark matter candidates, like, for example, axions. So we'll have 3 slides now. These are some of the radioastronomy receivers that we have designed. They cover a large part of the spectrum between 2 gigahertz and 90 gigahertz, which is the coverage of the 40-meter radio telescope. There is a gap here, which is due to the oxygen line, so we cannot observe here. This receiver, according to the scientist that leads the project about the discovery of molecules, is the best in the world. That's what he says, and I agree with him, of course. Well, for example, this one is for the Vigos receiver. This is the Vigos receivers that you use for geodetic observations. These are top quality receivers. Then we have very important developments. This is cutting edge technology. These are amplifiers. We have exported more than 1,000 amplifiers all over the world. As I said, they are embarked in space missions. They are in the Atacama Large Millimeter Array, in ALMA. They are in several observatories across the world. You will be able to visit today the amplifiers lab and also the receivers lab. And then the last slide is something I wanted to say, and it is that, as I said, radio frequency interference is a threat for radioastronomy. It is not also a threat for radioastronomy. We also have problems in optical astronomy. So we have started in the last years some works to monitor the interference, the effects of interferences like this one, and we have applied some mitigation methods. I'm not going to explain the slide because it has a lot of content, but just take this. We have a system which monitors the sky in different frequencies, and we monitor this just to try to implement some mitigation measurements and to learn about it. And then there is a third leg that we have at the observatory, and is we want to become a fundamental station, a geodetic fundamental station. For that, we have BLBI. We have been observing since 1992 with a 14-meter telescope, then with a 40-meter since 2008, and we have been also observing since 2016 with a 13-meter telescope. We have 2 GNSS receivers, which are integrated in international networks, and then we have now the satellite laser ranging station. I took this picture yesterday. So you will be able to visit this this evening. And then I have to finish my presentation because I have to acknowledge the funding agencies, of course. So as Beatriz said, we can take part, we are one of the singular infrastructures, scientific and technical infrastructures of Spain. There are 29 of those, and we are one of those. To become in this private club, you have to have an open skies policy. So that means you have to be open to the world. So we get these funds, and we get these funds from Europe. We get 80% of the funds 80% of the funds are from Europe, 20% are from Spain. We have 2 projects, Hidalgo and we have INART. Hidalgo is for laboratories, workshops, and equipment for developments in radioastronomy, and also for the new SLR station. Basically, all the funds that we have for the station come from here. And then we have another project with 3.7 million euros, which are improvements in the 40-meter radio telescope, and also a new BLBI software correlator, which will help in the Vigos project, and which will be the correlator for the RAEG network. And we plan, and we have to, finish by June 23, because this is what Europe tells us. And that's it. Okay, thank you.
Thank you very much, Pablo. Now, we would like to get some questions from either the audience or online. I think we have
Yes.
one online. So, question for Pablo from Frank Lemoyne.
Yes.
Has the 4D-meter radio telescope ever been used to track or study near-Earth asteroids? That's the question number one. And question number two, do you ever do joint observing sessions with the nearby NASA Deep Space Network stations at Madrid?
Okay, we have never tracked near-Earth asteroids. I think, well, I don't know if radioastronomy has been used for that, except maybe with Arecibo, which was used, I think it was used as a radar, and you can see the reflection of the NEAS. And about the other question, yes, we have taken part not only on pure radioastronomy observations, but we have also tracked some space probes. That's right. We have, for example, tracked Mars Express because we wanted to make some physical experiments. We wanted to see how we could see the Doppler effect coming from the accelerations of the space probes near the sun planets, Mars and Venus. We also tracked a space probe which was Huygens, because there was a descent in one of the satellites of Jupiter, I think it was, but that was long time ago. And sometimes the space agencies have asked for us for some collaborative observations, but I cannot say anything about that. Okay. Once with Juan Daniel, by the way, we were looking at the Voyager 2. It was fun to do that. Yes, we could detect it with the 40-meter radio telescope. It was a very nice observation. You can ask him today. He's the head of the engineers of the Amplifiers group in Yebes. Yes. Is there any other question?
Thank you.
No?
Someone from the room?
Yeah. Yes.
Okay, one fundamental question. You showed this image of the center of the galaxy in the beginning, and I just wanted to make sure I got it right. So the secret is that there's dust so that you cannot see the objects at the center and the visual wavelength.
Yes.
But if you look at the radio, then you see all those
yes.
things popping up. Okay. And then there was this colorful picture on the next slide, and I guess it was the same region. That was correct? The center of the galaxy?
Yeah, I showed two pictures.
Yes.
One was the dark background with the stars, and then you could see another picture which had a lot of colors, as you said, with lots of supernova remnants. Yes, it is the same region, exactly the same. I prepared the first image so that it could match exactly the second one.
Okay, thanks. And this is also a rather basic question, I think, but what are all those colors? Is it just a measure of the intensity, or is there
it is a measure of the intensity. Of course, they are artificial colors.
Yeah,
sure.
But colors are just nicer to look at.
Yes.
All right.
Yes.
Thank you.
One more question.
Thanks for the nice talk. Yeah, I've just recently noticed that there are some radio telescopes available on the amateur astronomy market. I mean, what do you think in general of such, let's say, low aperture, relatively cheap for amateur astronomy telescope? Could that somehow contribute in any way to scientific aspect, or would it just be a, I don't know, some stupid ideas of amateur astronomers?
You are talking about amateur radio telescopes, you said, not optical telescopes.
Radio, yes. I mean, there's something in the, like, okay, for a single person, a little bit more expensive, of course. But in the area of 50K
well,
euros.
you got me here. I don't know what to answer. I'm surprised because I don't know if they are very useful, because if they are small, the angular resolution is very poor, and then you will get a lot of objects in your beam. So I'm not sure that they are very helpful, unless you decide to create an array with small telescopes. But this is much more complex. In that case, yes, it would be interesting, but because, for example, you could monitor changes in amplitude with effects which are periodic or are variable. That could be interesting. And in fact, I will say something about this, and it is that optical telescopes from amateurs are very important because they complement some observations that we do in radio. For example, with evolved stars. The evolved stars contract and expand, and you can monitor the changes of the luminosity with amateur telescopes. And they are very helpful because they complement some radio observations done with spectral lines, like, for example, silicon monoxide. But for radio telescopes, I didn't know.
Okay, thanks.
Okay.
Good. Thank you.
We don't have any more questions, so thank you again, Pablo, for this very nice talk.